Hello learners, welcome to today's revision class. Today we'll be revising a topic in Form 4, that is floating and sinking. We will be doing the numerical questions in the KLB. Right away, number 1, we have question C, which reads, a glass block of weight 0.7 Newton is suspended by a string in water. If the block is completely immersed and the tension in the string is 0.45 Newton, find Roman 1, the upthrust on the block, Roman 2, its density. Okay, so this is the approach we'll give the question. We have a glass block. I'll sketch the glass block, me here. So it is suspended. This is my string suspending the glass block. My glass block is also completely immersed. I'm just going to sketch the perfect diagram such, and this block is inside liquid. So we are told that it is completely immersed. It means it is completely covered by water. So all this is water covering the glass block. Then we are told that the weight of the block, W, is equals to 0.75 newtons. Another information given is that the tension on the string that is supporting this block is 0.45. So this is the fixed point. So the tension is acting in this direction towards the fixed point. That is the tension force T. We are told that T, that is the tension, is 0.45 Newton. Okay. The first question was to get the upthrust. Before I get to that question, I want to indicate the forces acting on this immersed block. Because the block is immersed, it is experiencing another upward force called upthrust. Upthrust acting upwards. There is also a downward force, which is the weight of this block, W. So when you look at these three forces, that is the tension, upthrust, and the weight, these forces are balancing. And you have two forces acting in the same direction, that is the tensional force and the upthrust. Weight is acting in the opposite direction, but the three are balancing. So according to this relation, you can say that tensional force plus the upthrust is equals to the weight. That is equals to the downward force here. Now we need to get the upthrust. The first question was to get the upthrust. Mathematically, upthrust will be weight less tension, and therefore upthrust is equals to, the weight here is 0.75. I subtract the tension force, which is 0.45. 5. Okay, once that is done, we'll get our upthrust, which is 0.30 newtons. So that is the upthrust on the block. The next question is calculating the density of the block. The density of the block. So Roman 2, we are supposed to get the density of the block. Density of the block. Okay, now to get the density of this block, we will first of all give it this approach. We know very well that density is given by mass divided by volume, where this one is mass of the block and M here, V here is the volume of the block. Now, we can get the mass of this block because we are given the weight of the block up here, but whatever is lacking is the volume of the block. So to get the volume of this glass block, we give it, or we get it from the upthrust. Upthrust U is given by V rho G, where this V is the volume of the liquid displaced, which is the same as the volume of the block itself here. Rho, this is the density of the displaced liquid, in this case water, and then G is a constant. But then our upthrust, we had calculated above here, so we take it here and we substitute. During substitution, we'll have 0.30 is equals to V. This is the volume we are looking for, which is the same as the volume of the block, and is also the volume of the liquid displaced. I multiply by the density of the liquid, which is water. The density of water is 1000 kilogram per cubic meter. Then again I multiply by 10, which is G, is a constant. On this other side I have 0.30 equal to 10,000 V. Divide both sides by 10,000. So we obtain our V to be 3 times 10 power negative 5 3 times 10 power negative 5 cubic meter. So that is the volume of the block, which you obtained just from the upthrust. Now we need to get mass of this block. You know that mass is related and with weight with the following. Mass is equal to weight divided by G. You already told that the block weighs 0.75 newtons. So I come and say that 0.75 newtons divided by G, which is 10, and my answer is 0.075 kg, that's kilogram. From there, I have all the parameters that is required to get the density of the block. I have the mass with me, I have the volume with me, so I can go ahead and get the density of the block. So density of the block is given by mass divided by volume. And my mass is 0.075 kilograms divided by 3 times 10 to the power negative 5, of course, cubic meter. When you divide that one using your calculator, 0.075 times 3 divided by 3 times 10 to the power negative 5, Okay, we obtain 2,500 kilogram per cubic meter. So learners, this is the density of the block. Question 2, it reads, a solid of density 2.5 grams per cubic centimeters is weighed in air. When the solid is completely immersed in water in a measuring cylinder, the level of water in the cylinder rises from 40 cubic centimeters to 80 cubic centimeters. Determine A, the volume of the solid, and B, its apparent weight. Okay, learners, we have a solid here whose density is known, and the solid is immersed in a measuring cylinder that initially had water at a level of 40 cubic centimeters, and upon immersing this solid, the level of water rose from 40 cubic centimeters to 80 cubic centimeters. The first question is to determine the volume of the solid. Okay, so the first question, this A, we are to determine volume of the solid. Okay, so that's what we are looking for. And before then, we can sketch what's happening by we can do a sketch here. This is our volume, measuring cylinder, and the measuring cylinder. So initially the level of water in our measuring cylinder was 40 before the solid was immersed. So we can assume this is where the level was before the solid was brought. So this is 40 cubic centimeters. Then we are bringing the solid now. This is our solid. And then since the solid has been immersed, it seems that there was maybe a spring balance, of course, to tell us something to do with the apparent weight. So water rose up to this level, maybe we assume it was at this level, which is 80 cubic centimeters. So this is water displaced as a result of the solid being immersed here. Okay, the first question is to get the volume of, basically at a glance, this is a displacement method of determining volume of solids, and therefore I'm just going to say that volume of this solid will be V2 minus V1, where our V2 is this one and our V1 is this. So the difference will give us the volume of the solid. So that one will be 80 minus 40, and that one gives us 40 cubic centimeters. We were not told to give our volume in SI unit, but you can simply convert this one into SI unit. I just multiply 40 by 10 power negative 6 cubic meter. I've converted a cubic centimeter to a cubic meter, and this this one can be again rewritten as 4.0 times 10⁻⁵ cubic meter. So this is the volume of the solid. Question 2, that is part B, we want to get the apparent weight. Apparent weight. So to get the apparent weight, that is part B. Part B requires us to get the apparent weight. So before we determine this apparent weight, first we will ask ourselves or we'll just make a recap of whatever we had learned in Form 1, that when a body is immersed in a fluid, it experiences an upward force. This upward force is what we call the upthrust. So there is a relationship between upthrust, the weight, and the apparent weight. And these two are related by the following formula. I will say weight, that is weight in air, equals to upthrust plus apparent weight, which I'm calling WAP, apparent weight. So if I'm looking for apparent weight, the upthrust will cross over this side, so that I subtract it from the weight in air to get my apparent weight. So therefore, this one implies that apparent weight equals to weight in air, we subtract upthrust. Said and done, we are now left with one thing. We want to know the weight of this solid. So weight of the solid, that is W of solid, is given by the volume of the solid multiplied by the density of that solid, we multiply by G. If you check from the question, were we given the density of the solid? The density is given here, and it is in grams per cubic centimeter. Therefore, we need to use it here in the right unit, that is in the SI unit. The volume already, the volume of the solid we have, it is here, and it is in the right unit, the SI unit. Okay, so let us just go straight away and get the weight of this solid, which is simply 4.0 10⁻⁵. I multiply by 2500. 2500 in this case is the density of the solid, but in the SI unit, just multiply it by 1000. We shall have converted it into kilogram per cubic meter. Then we also multiply it by 10. Once that is done, using your calculator, you multiply the 4.0 times 10⁻⁵ by 2500 by 10, you get 1. That's 1 Newton. 1 Newton. So we have weight in air, which is the weight of the solid here. We are not having the upthrust. For upthrust, we can get upthrust using this relationship. Upthrust on the solid. The solid is experiencing an upward force, which we are calling upthrust, denoted by U. So at that particular point, we need to get upthrust. So upthrust is given by V rho G, where this V is the volume of the fluid the solid has displaced. Because the solid is totally immersed, it is the same as the volume of the solid itself. Rho here is the density of the liquid displaced here, water, and G is a constant. So straight away we get our upthrust, which is 4 10 power negative 5. It's the same as just this value here. We multiply this one by the density of water, 1000. Then we multiply by 10. Once we do that, we shall get our upthrust. So using the calculator, multiply 4 times 10 power negative 5 times 1000 times 10. You get 0.4 newtons. So learners, we have the weight with us of the solid. It's the same as weight in air, weight of the solid in air. We also have the upthrust, that is the upward force acting on the solid. Now we come and apply this formula in this one. We substitute them here to get the apparent weight. So we had said that apparent weight, that is WAP, is given by weight in air minus upthrust. So our weight in air is 1 Newton. We subtract upthrust, which is 0.4 Newton. So we get from our calculator, this is a difference of 0. The difference is 0.6 Newton. So that is the upthrust, that is the apparent weight of the solid. Question 3. Question 3 reads, a balloon of volume 10 cubic meter filled with hydrogen floats. You can see I've underlined the word floats. There's a lot of information on this. Floats in the atmosphere. If the mass of the balloon fabric is 10.3 kilograms, calculate the density of the surrounding air. Take density of hydrogen to be 0.09 kilogram per cubic meter. Okay, learners, now we will give this question this approach. First, I will show the balloon. This is the balloon. So that is my balloon. So my balloon has got a volume of 10 cubic meter. The balloon is filled with hydrogen gas. Okay. I'm told that this balloon is floating in the atmosphere. So it means it is surrounded by air. It is surrounded by air. It's just the atmosphere. So air is covering around it like that. Another thing, I'm told that the density of hydrogen is given to be 0.09 kilogram per cubic meter. Apart from the density of the hydrogen, I'm also provided with the mass of the balloon fabric. So mass of balloon fabric. This is the material used to make the balloon, 10.3 kilogram. This one is 10.3 kilogram. So the balloon is made of some material, so these ones making the balloon has a total mass of 10.3 kilogram. Okay, so the next thing, we are told to calculate the density of the surrounding air. So first of all, let us get the weight of hydrogen gas inside this balloon. So weight, this W, over hydrogen gas, oh, this is water, no, sorry, this is H2, weight of hydrogen gas inside the balloon. We know very well that weight is given by volume multiplied by the density multiplied by G. So the weight here will be, volume is 10 cubic meter, the density of hydrogen is 0.09, then our G is 10, which are constant. So this one gives us 10 by 0.09 by 10, that is exactly 9. So it is 9 newtons. So once we have that, we need to get the total weight of the balloon. But before then, we get the weight of the balloon fabric. So weight of balloon fabric. The weight of the balloon fabric is given by W is equals to mg. The mass of the balloon fabric was given to be 10.3. Let's multiply by 10, and we get that one to be 103 newtons. Once that is done, we can now go ahead and get the total weight of the balloon. So total weight of the balloon. So when I say total weight of the balloon, I mean the total downward force acting on this balloon. That is total downward force on the balloon. This is simply the sum of mass, the sum of weight of hydrogen inside the balloon plus the weight of the fabric. So that one will give us 103 plus 9. This is 112 Newton. So in short, from the diagram, there is that force acting downwards here on the balloon, this one. Its magnitude is 112 Newton. But then there is another force acting upwards, which we are calling the upthrust. Remember, I even said from the question that this word floats is very important. So we are going to pick it from the law of flotation, and it states that a floating body displaces its own weight of the fluid in which it floats. And remember, from Archimedes' principle, a body experiences an upthrust. Whether it is partially or totally immersed in a fluid, it experiences upthrust equivalent or equal to the weight of the fluid displaced. So when you look at these two statements here, the principle and the law, for this body to float, it means the total upward force must be equal to the total downward force. And our total upward force is upthrust. So we say that since the balloon is floating, it implies that upthrust equals the weight, and our weight is the sum of the balloon fabric and also the content of the balloon. So upthrust equals to 112 newtons. Remember, the question we are asked is the density of the surrounding air, this air here. Upthrust is given by V rho G. So the upthrust a given body experiences is calculated using this relationship where V is the volume of the fluid that body is displacing. This is the same as the volume of the body itself, which in our case here is this volume here. Because if the balloon has a volume of 10 cubic meter, it displaces the same volume of air around it. The rho here, this is the density of the surrounding air, that is of the fluid being displaced. And G is a constant, so I will equate these two here. And I say V rho G is equals to 112 Newton. But what is our V? Our V is 10. 10. And then the rho, we are looking for the rho, and then this is another 10, which is 10, equals to 112. Again, this one becomes 100 rho, which is equivalent to 112. Divide by 100, divide by 100. Rho equals to 1.12 kilogram per cubic meter. So, learners, this is the density of the surrounding air, which we are told that calculate the density of the surrounding air. So that's the density of the surrounding air. Number 4. Number 4 reads, a glass tube has a uniform cross-sectional area of 4.52 square centimeters. It is weighed and floated in a liquid. The weight of the tube immersed in the liquid is, the length of the tube immersed, meaning the length of the tube immersed in the liquid is 16 centimeters. If the mass of the tube and its content is 80 grams, determine the density of the liquid. Determine the density of the liquid. Okay, let me now draw so that you can see at a glance what's taking place. So I will have my tube right here. And of course it is floated in a liquid, so we want to assume that this is the container containing the liquid. Container containing the liquid is this. Yes, just come and balance. So the container has got some liquid. We don't know which type of liquid. Just stored the liquid. The cross-section area of this tube A, we are told to be 4.52 square centimeters. And then we are told that it is weighed and floated in a liquid, and the length of the tube immersed in the liquid is 16. So I will assume that the 16 length here I'm talking about is from this point, which is now that, to this point. So this is the 16 centimeter length. 16 centimeter length. Okay, so this is a liquid whose information we don't know. And then we are told that this tube and its content weighed 80 grams. So for this tube normally to float upright, it must have some materials here. You see the content we're talking about? That's the content. So that's the content of the tube. And then the question now, determine the density of the liquid. And then there is another important point here, floated. Okay, so the first approach, we want to know the volume of the liquid here displaced as a result of this length of the tube being immersed. Of course, because this part of the tube is inside, what volume of this liquid was displaced? That is my first approach. Okay, so I'll start by can use this side to start. So I have mass, which I'm given to be 80 grams, and then I want to look for volume of liquid displaced. So volume of liquid displaced. Volume of the liquid displaced. And this one, I'm going to get it through this. I'll just have to multiply the cross-sectional area of the tube by this length that is under the liquid. The cross-sectional area is given in square centimeter, as well as the length is also given in centimeters. So when I multiply cross-sectional area by the length, I'll have my volume but in cubic centimeter, which I can later on change into cubic meter. So here we go. That one will be cross-sectional area 4.5 to multiply by 16. Remember, this one is in cubic centimeter, and when I multiply by 10 power negative 6, my answer will be in cubic meter. Using my calculator, can multiply 4.52 times 16 times 10 power negative 6. This one gives us 7.232. Becomes 7.232 10 power negative 5 cubic centimeters. Okay, and then after that, because I'm told that this tube, as you can see, it is actually floating. It is floating with part of it inside and part of it outside. From the law of flotation, I can just say from the law of flotation. A floating body displaces its own weight of the fluid in which it floats. Meaning, because this tube is floating, the weight of this fluid here, the weight of this tube is equal to the weight of the liquid or the weight of the fluid it is displacing. And even when you pick it from Archimedes' principle, when a body is partially or totally immersed in a liquid or in a fluid, that is, it experiences an upthrust equivalent or equal to the weight of the liquid displaced. So when I link the two, you'll agree with me that the weight of the liquid displaced here should be equal to the weight of this tube plus the content. That is according to the law of flotation, as you could see. As you could see from this one. This is the equation. Question 4. It is floated. So from that, I can come and say that therefore upthrust is equal to the weight of the body. Upthrust is equal to weight of the body because this body is floating. So a floating body displaces its own weight. So whatever is being displaced here is this liquid, whose weight is just upthrust. So I'll equal to the weight of the body, of the test tube now. So upthrust is given by U and weight W. Upthrust is given by V rho G and weight is given by mg. So in upthrust here, this V is the volume of this liquid displaced, which we have calculated up here. This rho is the density of this liquid, which is our question now, which is what we are supposed to determine the density of the liquid. It is our question. Okay, G is a constant, it is 10, we'll be using 10. This M is the mass of the tube plus the content, everything. This G here is also a constant, so let us substitute. V I've said is the volume of the liquid displaced, which is this 7.232 10 power negative 5. I multiply by the rho, which is the density of the liquid, which I don't know. I multiply by 10. This one should be equal to the mass is in grams. You cannot use it the way it is here. So you change this mass into kilogram. So I'll take 80. I multiply by 10 negative 3. You already converted into kilogram. Then I multiply it by 10. So once that is done from my calculator, this one will give me 7.232 times 10 power negative 4 rho equals to, when you multiply this one, you'll get 8.0 times 10 power negative 1. So to get the value of rho, in this case, I'll have to divide both sides by 7.232 times 10 power negative 4, both sides, the same this one, 0.232 times 10 power negative 4. So this one will cancel out. We have rho equals to, so when you divide 8, mathematically just divide this one by this, then we later on come and harmonize these powers, because we know when we have numbers of the same bases being divided, just subtract their powers. That can be done this side, but this one we just divide on this other side. So when you do that, you'll get 1.106 times 10 to power 3 kilogram per cubic meters. So learners, this is the density of the liquid in this outer container. The liquid, the density of this liquid that was being displaced by the test tube and its content. Let's move to number 5C. It is a numerical question. Remember, we are just doing numerical questions today. Number 5C reads, the figure shows a sphere of radius 3 centimeters, floating between two liquids A and B, so that half of it is in A, full stop. If the density of the liquids A and B are 0.8 grams per cubic centimeters and 1.0 grams per cubic centimeters respectively, determine the mass of the sphere. So you can see the diagram is this. Of course, I'll also sketch during calculation. This is liquid A, whose density is 0.8. Yeah, our sphere here, half of it is in liquid A and half of it is in liquid B. We are told to get the mass of the sphere. The mass of the sphere. Okay, learners, this is the same question. I've just sketched it here so that we may look at it at we can calculate at the same time. You can be referring to the diagram. This is liquid A of density 0.8 grams per cubic centimeter. This is liquid B of density 1.0 gram per cubic centimeter. The radius of the sphere here is 3. Now the first approach here is to get the volume of the sphere. The volume of the sphere. So volume of the sphere. The volume of the sphere is given by this formula, 4 over 3 pi r cubed. This is going to be 4 over 3 multiplied by pi multiplied by the radius cubed. And then, because the radius is given in centimeter, my volume is now in cubic centimeters. So to convert, I just multiply it by 10 to the power negative 6, so it becomes into cubic meter. So the volume of this sphere is, when you multiply all this using a calculator, you get 4 over 3 multiplied by pi, shift pi, multiplied by 3, multiplied by 3 times 3, that is 3 cubed, then 10 to the power negative 6 becomes 1.131, get 1.131 10 to the power negative 5 cubic meter. We were told from the equation that half of it, the half of it is in A, meaning half of this sphere is in A and the remaining half is in B. Okay, so the same to whatever we're going to do here. So get volume in A. So look at volume in A. Volume in A is simply a half of this. So we divide this one by 2, just divide this one by 2. We'll come and harmonize the power. Sorry, this one I did not, this one should be to power 4. Yeah, power negative 4. That is to power negative 4. So now divide this one by 2. You'll get 0 0.565 times 10 to the power negative 4 cubic meter. Now when this one goes back here, because it's not in standard form, we'll subtract 1 here. We are going to add negative 1, so that becomes 5.655 10 to the power negative 5 cubic meter. Once we have that, we can now get upthrust that this ball is experiencing when it is in liquid A. So upthrust in A. upthrust is given by V rho G, where this V is the volume of the liquid displaced. So the liquid A displaced is this, the volume of liquid A displaced is this. We've calculated above there, which is 5.655 10 power times 10 power negative 5, and then just multiply it by the density of liquid A. The density of the liquid A is not in the right unit, so we multiply it by 1000 to convert it into SI unit, so it becomes 800, and then multiply it by 10. Once that is done, we get the upthrust to be 0.4524. Multiply this and get 0.4524 newtons. We go to volume of the sphere in liquid B. So we say volume in B. The volume in B will be the same as this one because the sphere was half of it was in B and half of it was also in A. 10 power negative 5. From there, just go to upthrust in B. The upthrust that is acting on the sphere when it is in liquid B. We know that upthrust is equals to V rho G. So upthrust there will be the volume displaced, 5.655 by 10 power negative 5. I multiply by the density of liquid A and liquid B, which are 1.0 grams per cubic centimeter. We change into SI unit, becomes 1000. Just simply multiply by 1000. And again, we multiply it by 10. Once you do that, you get your upthrust to be, and you multiply that, you will get the upthrust to be 0.5655 0.5655 newtons. So that is not the answer. That is not the answer. Remember, we are supposed to calculate the, let me check, determine the mass of the sphere. So it is the mass of the sphere. So we are not yet there. Now we get the total upthrust acting on this sphere. Total upthrust. So total upthrust. It will be upthrust due to A plus upthrust due to B. And that is 0.4524 plus 0.5655. And this one will give us the sum of the two is 1.0179. 1.0179 newtons. We are told that the sphere was floating in these two, and we know that a floating body displaces its own weight of the fluid in which it floats. So this is the weight of the sphere. So we just say that from the law of flotation, upthrust equals weight. But our body was floating in two different liquids, liquid A and liquid B. So their total upthrust is this one. So we say 1.0179 is equals to W, which is weight. But I need mass. Because I need mass, I divide both sides by G. So divide this one by G. Divide this one by G. So W over G is normally mass. And our G is 10. So 1.0179 Newton. Just divide by 10. And therefore, the mass is 0.10179 kilogram. So that is the mass of that sphere. Okay, thank you for watching. Kindly, for the new learners, subscribe, share, like and comment on our revision videos. And remember to tune for our next episodes. We'll be going to the next episode, that is we'll be doing number 6, 7. We'll also do 7 part B. We'll also move to learners. We'll also go and do this together in our next videos. We will do this, we'll do this one before we go to another chapter. It may not be this, but it can be any other that is having numerical questions to the Form 4s. I still wish you all the best as you prepare for your KCC. Thank you.